Thank you, Mr. Chairman. Today, I would like to talk about simulation of a ridge-type semiconductor laser with transversal diffraction gratings. The background of the present work is shown here. The theme of the present work is a high-power 980 nanometer semiconductor laser which is used to pump erbium-doped optical fiber amplifiers. In this laser, diode, cladding, and guiding layers are aluminum gallium arsenide layers, which are oxidized easily during etching processes. The oxidized aluminum gallium arsenide layers highly degrade electrical and optical characteristics of the high-power 980 nanometer semiconductor lasers. To avoid these problems, ridge structures are adopted. To avoid the problems caused by oxidization of aluminum gallium arsenide layers, ridge structures are adopted. In the ridge structures, higher-order horizontal transverse modes as well as the fundamental horizontal transverse mode are confined to their waveguides. Therefore, with an increase in injected current, higher-order horizontal transverse modes lays, kinks appear in their current versus light output curves. The purpose of the present work is to achieve single horizontal transverse mode operation with kink-free operation in a ridge LD with a wide mesa. The slide compares with the conventional ridge structure and the proposed structure. The proposed structure has transversal diffraction gratings at the both sides of the mesa. In a conventional ridge structure, the first-order mode is confined under the mesa with gain. In the proposed structure with transversal diffraction gratings, the first-order mode is confined under the grating with loss. This slide shows operating principles. The vertical line shows the refractive index, the horizontal line is normal to the cavity axis and the direction of the epitaxial growth. Figure A illustrates the distribution of the refractive index of a conventional ridge structure. Figure B draws the distribution of the refractive index of transversal gratings. Figure C reveals a coupled distribution of the refractive index of the ridge structure and the transversal gratings. Both the ridge structure and diffraction gratings make the light waves resonate. In general, the wavelengths of the resonant modes of the ridge structure are different from the wavelengths of the resonant modes of the diffraction gratings. We design the waveguide so that the wavelength of the fundamental horizontal transverse mode of the ridge structure and that of the diffraction gratings may agree with each other. As a result, only the fundamental horizontal transverse mode is confined to the waveguide with optical gain. The near-field patterns of the horizontal transverse modes are obtained by Fourier transform of the optical spectra. So, small wavelength difference between the resonant modes leads to a large difference in the peak positions of the near-field patterns. Therefore, the higher-order horizontal transverse modes are located at a region with optical loss while the fundamental horizontal transverse mode exists in a region with optical gain. Please note that the transversal diffraction gratings are used in the total reflection condition. On the contrary, diffraction gratings in DFB or DBR semiconductor lasers are used in the condition far from the total reflection condition. This figure shows a schematic cross-sectional view of the facet. The mesa width W is 5 microns. Please note that the mesa width of 5 microns leads to kink in IL curves for conventional ridge-type semiconductor lasers. The height of the mesa is 1.55 microns and width of the base is 60 microns. The cavity length is 1,200 microns. Power reflectivities of the front and rear facets are 2 and 90%, respectively. Injected current versus applied voltage curves are shown here. The parameter is the number of the grating periods n at one side of the mesa. The broken line shows the result when n is 20, the solid line shows the results when n is greater than 25. Please note that the IV curves when n is greater than 25 are overlapped. A differential resistance when n is greater than 25 is lower than that when n is 20, because the diffraction gratings contribute to confinement of the carriers below the mesa. This figure shows injected current versus light output curves. The parameter is the number of the grating periods n at one side of the mesa. The broken line shows the result when n is 20. The solid line shows the results when n is greater than 25. Please note that the IL curves when n is greater than 25 are overlapped. When n is 20, a kink appears in IL curve with oscillation of the first order horizontal transverse mode. When n is greater than 25, kinks do not exist in IL curves and only the fundamental horizontal transverse mode oscillates up to the injected current of 3 amps. The slide shows the distribution of the electron concentration when the injected current I is 1 amps. The vertical line shows the electron concentration, the horizontal shows the horizontal position. The origin is the center of the mesa. The transparent carrier concentration is 1.2 times 10 to the 18 th power per cubic centimeters. The electron concentration at the center of the mesa is lower than those in the both sides, because of the spatial hole burning. At the center of the mesa, the electron concentration when n is greater than 25 is lower than that when n is 20, because the electron consumption due to stimulated emission with single transverse mode operation is larger than that with two-mode operation. This figure shows near-field patterns for the fundamental horizontal transverse modes. The injected current I is 1 amps. The near-field patterns almost overlapped. FWHM is 3 microns, irrespective of existence or non-existence of kink. Since the core radius is 5 microns, high coupling efficiency of the laser beam to the erbium-doped fiber is expected. This slide shows near-field patterns for the first-order horizontal transverse modes. The injected current I is 1 amps. When n is 20, the near-field pattern for the first-order horizontal transverse mode exists in the optical gain region. This leads to kink in IL curve. When n is 25, the near-field pattern exists in the optical loss region. This leads to kink-free operation. Threshold current for the fundamental horizontal transverse mode is plotted as a function of the grating periods n. The threshold current has the lowest value when n is 40. In the next slide, threshold current is considered by overlapping of the optical field and the optical gain. We define the convolution H of the light distribution and the electron distribution by the equation on the right side. Here, I is relative light intensity, n is the electron concentration in the active layer, and L is the base width. This figure shows the convolution H of the light distribution and the electron distribution for the fundamental horizontal transverse mode. The injected current I is 40 milliamps, lower than threshold current. The convolution H has the highest value when n is 40. This leads to the lowest threshold current. This figure shows the convolution of the light distribution and the electron distribution for the first-order horizontal transverse mode. The injected current I is 1 amps. The convolution H has the highest value when n is 20. This leads to kink in IL curve. Please note that the convolution H when n is greater than 25 is lower than when n is 20. Finally, I would like to summarize my talk. To improve kink levels, a ridge-type semiconductor lasers with transversal diffraction gratings was proposed and simulated. It is found that kinks do not appear when the number of grating periods is greater than 25 for the mesa width of 5 microns. In this case, the first-order mode exists in the optical loss region. Thank you very much for your kind attention.